Okay, I think we could continue with this lecture about the equation of state. Let me just remind where we stopped. So I think we stopped there. And in a way, so the idea was just to show you an example of agnostic equation of state, so that you understand or you figure out what does it means. So do you have any question about that, or any remark that you made to yourself about the characteristic of this kind of equation of state? Yes. So how accurate? So that's a good question. And actually, maybe the next slide, I mean, it's a very nice transition to the next slide. So the next slide represents the mass and radius relation that you obtain if either you take the original equation of state, or you take a parameterized version, like a piecewise polytrope of this equation of state. Okay, so you can say, well, I have a table with an equation of state, and I solve the TOV as what you did 2 or 3 days ago. Okay, you read the table and you solve the TOV equation of state, the TOV equations. Or you say, well, I would like to estimate if this piecewise polytrope approach is accurate, and instead of solving, of having all the information which are in the table, I will capture a few of this information and translate it in the form of a piecewise polytrope. And the difference are the difference between the solid and the dashed lines. Okay, so it's not perfect, but then you have to wonder what is the imperfection of the uncertainties that we could tolerate. And of course, if we know exactly mass and radii of neutron stars, we would tolerate no uncertainties. But we know it with error bars. So the question is whether it is acceptable to have such uncertainties, considering the experimental error bars, for instance, or if we need better approaches. And you can see, for instance, so here this is a typical uncertainty in the radius. So it is a few hundred of meters. And I have added a slide at the end that shows the experimental uncertainties. And at the present time, I mean, we know the radius of a neutron star at 1 or 2 kilometers. Okay, so what it means is that with respect to the radius, I mean, it is still very acceptable to have uncertainties of the order of 100 meters, because we cannot measure radii of neutron star better than a few kilometers. And then there is also the other uncertainty, which is the uncertainty in the mass that you can see here. And presently, I mean, we discussed about the mass. So there is a mass distribution, and the upper mass is about twice the mass of the sun. But there are also uncertainties there, and such differences are also quite acceptable. So the piecewise polytrope is not perfect, that for sure. They can be improved if you increase the number of pieces. Okay, so for instance, here there are 3, 1, 2, and 3 density intervals, where in order to map the Equation state, and this figure have been generated with these 3 intervals. But you may imagine that, for instance, you decrease the intervals, and then you increase the number of layers, and there is and the more layers you have, the more accurate it will be. Okay, so but the condition will be that you will have also more parameters to fix. So you have to balance the number of parameters versus the accuracy, and you have to fix this number of parameters so that the accuracy is acceptable, and most probably with time, as the experimental uncertainties, the experimental error bars will get better and better, then you will increase the number of points in this kind of agnostic approaches. And these things are going together. Okay, so it's I cannot give you a definite answer. It's an answer which depends on time and which depends on the possibilities to measure more and more accurately the radius of neutron stars and the mass of neutron stars. But another thing that I would like you to realize is that when you have a piecewise polytrope or something which looks like that, of course you represent the function how the pressure depends on the density, but nowhere here I have explained what is the matter composition. So nowhere here in such approach, you have to say, well, the matter is made of neutrons, or the matter is made of quarks, or hyperons, or whatever. In fact, you in such approaches, agnostic approaches, you write a mathematical relation between the pressure and the density, but you don't know what are the particles which create this density. So it is very powerful to analyze the data, but it is totally agnostic in matter composition. So you don't know what the matter is made of. Okay, so there are things that you can better determine. So for instance, the equation of state, but then you still need some microscopic model. You still need to know, to infer the properties of matter and the interaction. And the nice thing that it provides is that instead of mapping microscopic calculations directly to experimental data, you can use these agnostic approaches in order to represent, for instance, an equation state from the data. And then you can map your macroscopic calculation to the equation of state compatible with the data. Okay, so in a way, it allows to simplify the link between theoretical calculations and data by representing the data in a form that is more suited to be compared with theoretical calculations. So like, for instance, an equation of state. Okay, so this agnostic approach does not resolve or does not answer fully the question that you have, which is what is the composition of matter, but it provides a very useful tool in the search, in the try to answer this question. Okay, yes. Yes, okay. Yes. Mm-hmm. Yes. Okay. Yes. So let's take, for instance, so you see here you have an equation of state, okay, this one, which clearly is stable because the gradient of the mass is positive, And then you have, let's take the dashed line because it is more pronounced. You have a small region here where you see that it is unstable. And then after it is stable again. Okay, so this second stability region is indeed called the second branch. And it may be obtained, for instance, if you have an equatorial state with quark matter, and then you have a first branch without quarks, and suddenly quarks appear. When they appear, they first destabilize the star. So that could be the reason why you have an unstable branch here. And then after, when they are numerous enough, then you have a stable system which appears again, and you have this stable branch. So your question is, suppose that I take, because you have to think that only the stable branch are physical, because the unstable just mean that your system collapse. So your question is, suppose I take this stable branch here and another stable branch here, and you see clearly that for a given mass you have two radii. But then you have to think about how you produce, how you produce these stars, for instance. And in the way you produce them, you see, for instance, that you enter here, okay, then you accumulate mass. And then what you do is that you jump here and you continue there. So in fact, the region of the second branch, which is of interest for you, is not the full region. It is a one for which you have a one-to-one relation between mass and radius. So you exclude the region where you have, for the same mass, two radii. Yeah. Yeah, you can represent you are totally allowed to represent the two stable branch, but you have to know that in the second branch you have to exclude the part for which you have two radii for the same mass, because you have to imagine how the system evolves. Yep. Well, okay, but yeah, I mean, in principle, you are right, but we have never seen any neutron star emitting mass. So, the physical system is going in one direction, and it's not so much accretion. It's because it's pretty small, but it is more during the formation of the star, in the proto-neutron star. So when you have a core collapse that you may have, you may experience a second branch and a phase transition. Okay, and so here we represent a hydrostatical picture of what happens, but in reality it is hydrodynamical. Okay, so I try to explain in simple words how it evolves in a dynamical way, but there are some aspects of the problem that are not described here, which are, for instance, the finite temperature, the presence of neutrino, and so on and so forth. So to give a more precise answer to your question, you should look to hydrodynamical simulations. Okay, but more or less, if you want to translate it in terms of hydrostatic solution of the general relativity, this is more or less what happens. You have to exclude in the second branch the region that corresponds to another radius for the same mass. Any other question? Okay. Yeah. So then there are. I mean, there is not a single agnostic approach. There are several ones. So I discussed piecewise polytropes. I think I will go a bit fast on the sound speed, just not to be too much delayed in my schedule. So if you want, you can still have a look on the slides if you are interested in them. So I provide you the slide, but I will not enter too much into the details. The idea here is, instead of mapping the relation between the pressure and the density, you map the sound speed, how the sound speed evolves with density. Okay, and the sound speed is defined as the derivative of the pressure. So in a way, what you control is not the pressure, but the derivative of the pressure. Okay, and you could imagine that in the same way as you were able to infer the equational state knowing the pressure, you are also able to infer the equational state if you know the derivative of the pressure by doing some integration and yeah, and that's the point. Okay, so I think I will not elaborate more on the sound speed model, but I just wanted to flash it and there are also others. Okay, so I will not make a list of all the agnostic approaches, but just give you an example. So just an illustration. So suppose that you have, for instance, that you randomly toss. Okay, so there we plot, for instance, sound speed as a function of the density. And if you follow just one color, so let's follow, for instance, the blue one. Okay, you see that sound speed, for instance, is tossed randomly. So you take a random number between 0 and 1, okay, in order to ensure stability condition. Or you can follow, for instance, the pink one where you have where it also going down and oscillating a lot. Okay, so you may say, well, I don't know anything about the sound speed, so I will toss randomly some random evolution of the sound speed. And then once I got the sound speed, I reconstruct the equational state. And this is an example. Okay, for each of these lines that are given here, you have the pressure versus the energy density generated by this random toss. Okay, so for instance, if I take the solid black line here, then I resolve it, I will have this equational state. And if I take the pink one, which is there, then I will have another equational state, which is here. Okay, so this is just to illustrate that it is possible and it is working. And then you could map the equational state into mass and radius, okay, by injecting this equational state and solving the TOV equations. And therefore the solid line which is there generates this equational state and generates this mass radius relation. Okay, so you see that it's working pretty well. Okay, and then we can start to discuss a bit more about observational constraints. And here, in this figure, you see the very few constraints we have. Okay, so the first one, we mentioned it a little bit, it is the maximum mass. So we know that the maximum mass should be above 2 solar mass because of radio astronomy. So we observe pulsars and we found that some pulsars have a mass which is above 2 solar mass. So we know that the equational state that we generate should predict that the maximum mass is above 2 solar mass. Okay, so this is the lower limit of the maximum mass. And then we know also from gravitational wave observations, and in particular from an event that occurred in 2017, the first detection of a merger of a neutron star, that since the mass of the two initial neutron stars is very well known, and the sum of the mass is about 2.6 solar mass, we know that after the fuse, there were some ejection of mass, but it's very small compared to the mass of the system. So they have created a super heavy neutron star who could not sustain its mass and collapse to a black hole. So we know that the upper limit of the maximum mass is about 2.6 solar mass. Okay, so we have an interval on the lower limit, and we have an estimation of the upper limit. And we don't know more accurately what is the maximum mass of a neutron star, but it should lie in this band with respect to the present knowledge. So that's already something, okay? And you see, for instance, in this figure, so you had a lot of equatorial states, and you see that there are a lot of equatorial states that does not satisfy this simple requirement, and they are all in gray. And the one that goes inside this band, you see from our construction, they are green here, and they are not so numerous. So you could use this this rule in order to select equatorial states, and it actually works because, so let's say that okay, so let's introduce a word that you certainly know. This is a prior. Okay, so all these are represents our prior equatorial state. And once we apply, we filter the equatorial state with respect to a single data here, then we have what we called a posterior, which is represented in green versus gray. And the posterior are the ones that survive the condition that we apply here. Okay, so this is the first, let's say this is the most acceptable condition that equatorial state should fulfill, is that they predict maximum mass, which are between the lower limit and the upper limit of the maximum mass, of the observed maximum mass. You have a question? I don't know. Sound of something. So you may hear something, but you don't know what are the particles that propagate this sound. Okay, so this is why it is called agnostic, because you cannot say it's propagated by hyperons or neutrons or whatever. You are ignorant. Yes. Yep.
See this curve, we can go back to the field south and not with 100% certainty we can indicate whenever this group belongs to quarter matter to hyperons of the electron.
Yep, because you have knowledge. Assume you don't have this knowledge. Assume you know, so you have knowledge due to your to your training, but assume that you are totally ignorant with respect to any microscopic interpretation of the sound speed, and assume that the only thing you know is the agnostic approach. Then you cannot say anything. But this is an illustration of what I was saying before, that this agnostic approach, they allow you to translate a data, which is a maximum mass or whatever, in an information that you can more easily compare with a knowledge that you have from microscopic approach. Okay, so it's a tool that reduces the distance between the model for dense matter and the data, because they are able to map some data, and data are diverse because we speak about maximum mass. Then we'll speak after that about radius, but we'll also speak about tidal deformability. And so they are diverse. They are not represented in the same space, but you want to use all these data and represent them in terms of an equation of state or of a sound speed or of something from which you can do some interpretation based on microscopic knowledge. Okay, so I think this is somehow the beauty of these agnostic approaches, but we have to realize that they are limited, because by themselves, they may say you have a bump in the sound speed, but they will never tell you why. And this is only you, with the knowledge that you have about microscopic approaches, which is able to say, well, there is a bump, and that I can interpret in this way from my knowledge. But the agnostic approach will never tell you what is the origin of the bump. Okay? So this is, because I'm not sure these things are very well understood. I mean, the fundamental differences between microscopic approaches and agnostic approaches. Most of people say, well, they are equivalent, and we'll work with only agnostic approach. And I mean, I like very much the agnostic approach, but I think you will not answer all the questions. Okay. So yeah, so we were discussing about the maximum mass, but so this is one data, okay. But there are also some mass and radii measurements by an observatory which is called NICER, and who have up to now observed two systems, two neutron stars, this J0030 and this J0740, and they produce typically contours that looks like that. And this is the reason why I told you, for instance, that the most accurate estimation of neutron star radii, okay, are about a few kilometers. If you just project vertically, this is what you obtain. So it's not very accurate, but you should imagine that it is the first data we have, and before they were useless or not very accurate estimation of the radius of neutron stars, or sometimes the radius was very model dependent. So you had to assume a model for the atmosphere of neutron stars, and then you infer the radius, but no one was able to confirm your hypothesis on the atmosphere of neutron stars. So this is somehow the first trustable uncertainties or contour that we have on mass and radii of neutron stars. So it's already something. And the people that are running this observatory promise that in the near future there will be at least one or two additional data that will be able to provide. Okay, so it's already something quite interesting. And you may say, okay, so my prior equation of state, I will also include this information in order to filter, to select the good equation of state. Okay, so all this, what does it mean, the good equation of state? So if you have an equation of state that goes, for instance, through this contour, then you say, okay, it's a good equation of state. So the probability that this equation of state represents the reality is 1. And but if it is out of this contour, like an equational state like that, then you will assign 0 or null probability to this equational state because it does not satisfy or does not reproduce your observation. But you can also cross-correlate. So you see that there are some equational state here which pass through one of these band, but does not match with the maximum mass. Okay, for this equational state, you will assign also a probability 0 because it represents only a part of the reality, but not all the data that we have. And then finally, we have this gravitational wave data from 1708-17, which was provided in terms of tidal deformability and is given here in mass and radii. So it is mapped from tidal deformability to mass and radius. What it says is that I mean, when you do this translation, so you say that you obtain an upper limit on the radius, okay, and so this box represents the upper limit. So all radii which are predicted on the left are accepted. But for instance, let's look at this group. All equational states that predict a radius which is larger than this prediction is rejected. Okay, it is not green. It is gray. Okay, so this is a way that this is a way you could use this agnostic approach in terms of masses and radius, in order to select from a prior knowledge, a prior set of equational states, the one that survives the constraints. They are in green in this plot, against the one that does not survive these constraints. Okay, is it clear for everybody? Good. So that allows me to enter into a new part, a new section of this chapter, which is addressing the question of how to compare theory versus data. Okay, how to do that in a more systematical way. Okay, so just general ideas about that. So imagine that you have a data. Okay, so what do I mean when I say I have data? So I mean that, for instance, some experimentalists or some observers, they provide an information in the form of a centroid, for instance, and an error bar. Okay, so this is the most general way that you can represent data. Okay, and then the centroid and the error bar. Okay, if you assume, for instance, that you have a Gaussian distribution, you can translate it, okay, in this way. And for instance, if the observer tells you that the error bar represents 1 sigma control level or 1 sigma uncertainty of in their analysis, in a Gaussian distribution, it means, so the 1 sigma, okay, so this if you assume, okay, if your signal is Gaussian, so it means that it is behaving in this way. So the x0 is the centroid, and the sigma, the s, is the width of your distribution. Okay, and if you say, well, my width represents 1 sigma deviation, it means that if you integrate your probability in this region, then you will have 67% of the whole probability. Okay, and 2 sigma is 95%, and so on and so forth. So usually, experimentalists, when they provide error bars, they say it's a 1 sigma, it's a 2 sigma, or it's a 90%, or it's a 50%. So they say exactly what represents this uncertainty. And if you take a Gaussian in order to interpret this uncertainty, then you can adjust correctly this S of your Gaussian distribution to map out correctly what is this uncertainty. So this is the most general way you can interpret, or you can determine what you can employ as a theoretician, for instance, the data which are provided by experimentalists or observers. Now, you have this data and you compare it to theory. Okay, so here, for instance, I give you 3 points. And you suppose that theoreticians, they are able to compute only a single point. So clearly, you have 1 point which is right in the center of your experimental uncertainty or experimental band, and you have 2 points which are out of it. Okay, so the first one, this one, clearly, you can say it is compatible with the data. Okay, so I think no one will be against this. Now the question is, you have points here that are out of the uncertainty, of the experimental uncertainty. So can you say anything about it if the theoretician do not provide you any uncertainty in their prediction? So is there 1 point? So can you say that this point is better than this one, for instance? Yes, it depends, but you don't have any more information than the one that I represent here. Okay, correct. So if you increase this uncertainty width, then if I understand correctly what you say, you will say, okay, at 2 sigma, this point is accepted, but at 3 sigma, this point is not. Okay. So you will say, okay, this is still an acceptable point, but this point is rejected. This is what you will say. Is that correct? Do I translate your answer correctly? Yeah. Yeah. So you will say, well, this point is more close to my uncertainty than this point, and therefore I may prefer this point over this point. So I think that this is the way. I mean, we have analyzed data for many years by just looking how close we are from the experimental uncertainty. But there is something from the theory which is clearly missing. It is the estimation of the uncertainty. So you don't have a theory without uncertainty. You have a theory, for instance, if you have a microscopic model, you do a SCRM, RMF, or whatever. Usually, the people who produce this model, they give you a set of parameters without any uncertainty, and they say you use this is SJ2 SCRM interaction with these parameters, and you don't have any estimation of how you are able to vary these parameters in order to be still compatible with the data which have been employed in order to fix these parameters. Okay, so there is no, historically, there is no estimation of the uncertainty. But you may say, well, maybe some of my model parameter, I could vary it a little bit. And if I vary it, what impact it has on my prediction? Okay, so this is what we call the systematical uncertainties. So the possibility to vary some, to induce some fluctuations in the parameters of the model, and the estimation of the consequence for a given observable or another observable from this model. And you may, for instance, obtain such result. Okay, so you explore the theoretical uncertainty in your prediction, and you find, for instance, that this point that you had before has, in fact, an error bar which overlap with the experimental error bar. However, if you explore the theoretical uncertainty for this model, you may have, it is an example, a much smaller uncertainty. And then you will come to a different conclusion. You will come to the conclusion that this model, so a fraction of this model, can overlap with experimental uncertainty, and therefore this model is compatible with the data at 1 sigma. But this model, for instance, which may look closer to the data, in fact, when you explore the theoretical uncertainty, you have no overlap with the data. So this model may be less compatible with the data than this model, even though this model is further, the centroid that you predict is further from. So it is just an illustration to convince you that it is extremely important to, when you have a model, to estimate an uncertainty associated to this model when you want to compare to data. Okay? The problem is that usually people, they have theories, and it takes days or more to obtain one result. And in order to, as I say, in order to explore the theoretical uncertainty, you have to repeat the same calculation 10, 100, or more, thousands of times, in order to estimate a distribution of prediction. So if you have a calculation that takes a week to give you an answer, and I tell you, well, now I would like to have an uncertainty, then you have to generate to redo the same work hundreds of times. So your result, you will obtain it not in a week, but in 100 weeks, so in 2 years, typically. So it's pretty time consuming. Okay. Yeah, so this is the limitation. This is the problem that theoreticians they face, and the question is that they need to speed up the calculation. So because you don't want to wait 2 years in order to publish your result, you want to make it faster. Okay, so for this reason, people have thought about trying to mimic in a faster way the prediction of the model by using, for instance, some emulators. So that's this is a way. So you generate maybe 10 or a few predictions, and then you employ an emulator which may be based on a neural network, for instance, that you train on your model. And once it is enough trained or well trained, then you replace the model by the emulator, which provides you in a fraction of a second the answer, and you don't have to wait for a week. Okay, so it's a way to speed up the calculation. Or another way is you could say, okay, I have a model which is quite complex, but I will replace it by a simpler model, an analytical model, which that I understand better and which is faster, and in which I can introduce in some ways the uncertainty due to the model. So in these two solutions, one is the emulator is using some modern computing approaches based on the neural network, for instance, and the other is more old-fashioned, but maybe more tractable because you are still generating a model. Okay, but you simplify in a way the model so that you can speed it up. So so this is an introduction to an approach that we have suggested recently for the equatorial state that is called the meta model. So in a way, the equatorial state, depending on how you produce it, could be very, very long. So if you develop some microscopic approach, you can obtain an equatorial state after several days, and you still face the same problem as before, which is that the single equatorial state is not what you expect. What you expect is a band of uncertainty, of probable, equiprobable equatorial states. And the meta model is an approach for the equatorial state, which in a way is able to mimic your macroscopic calculation in an analytical form. So for instance, as we've done, we have seen before, by employing the nuclear empirical parameters, we can expand the equatorial state in density for the symmetric part and for the symmetry energy. Okay, and you see here that they are the empirical parameters that appear. So in a way, if you can estimate the uncertainty on the empirical parameters from your macroscopic approach, you could employ the meta model in order to explore this uncertainty and generate a band of equatorial state compatible with this uncertainty. And this is what is done. And the advantage, as you can see, is that your mapping of your equatorial state is quite analytical, and therefore it is very well adapted for exploration of the possibilities of the uncertainties than if you use, for instance, a macroscopic time-consuming approach. Okay, so this is just an example. So suppose that you vary some of these empirical parameters and you translate and you compute the equatorial state, and then you inject it in the TOV equations, and you generate a family of mass and radii. Okay, so these two panels that I show here are possibilities. So, for instance, on the top panel here, okay, what is varied is the slope of the symmetry energy. So the different colors correspond to different slope of symmetry energies. So this parameter QSAT, which is there, okay, which is a skewness parameter, is fixed. Okay, and the different colors represent the slope of the symmetry energy, but then the incompressibility, the curvature of the symmetry energy is varied. Okay, and that raises. So, for instance, if you take the black color, the black line, so you see at low mass, which means low density, all the curves they merge. But if you increase the mass, if you increase the density, then you see that this parameter has, which appears as x to the square, raise a degeneracy for the equation of state, and then you produce, instead of having a single equation of state like that, so you start to see the difference which are due to the variation of the value of K-sim. Okay, so and these different dots here represent different values for the central density of the neutron star. So, for instance, about 1 solar mass, you see that the central density is about twice the saturation density. So the density inside finite nuclei. And when you reach about 2 solar mass, okay, so you are close to 3 times saturation density. So that tells you, for instance, that if you only employ finite nuclei to constrain the equation of state, what you are doing is constraining this region of neutron stars, so very low mass neutron stars, where in a region where no neutron stars have never been detected. But if you want to probe the upper limit of masses, then you need an equation of state that goes above your prediction or goes above central density of neutron stars by a factor at least 3. Okay, so that's so let me come back to this figure, to the discussion of this figure. So you can see that by varying these empirical parameters, you explore different paths, different ways, your mass and radius relation. And therefore, as we have seen before, if you have some data, some information that tells you, okay, this is the mass of neutron stars and the radii associated, then you could expect to be able to identify what are the empirical parameters which are best reproducing your observational prediction. And on the bottom panel, I still have a color which depend on the value of LSIM, but this time I vary QSAT. Okay, so this empirical parameter for which control the density dependence in symmetric matter, and the value of the curvature of the symmetry energy K-sim. So this parameter is fixed, and you see that you explore mass and radii, but in different ways. Okay, so we'll see right after that Bayesian approach, but you again, I mean, what this illustrates is that if you had some data which are accurate and predict you this set of points, then you can infer what is the best, what are the best empirical parameters that are compatible with your data. And these empirical parameters, you can translate it in terms of your microscopic approach that the meta model is simulating, but in a fast way. Any question? Yep. Well, the meta model can be predict something that you can directly compare to the data. So it is similar to the agnostic approach, but in a way it has some more ingredients, and for instance, you know what is the composition of matter. Okay. Yep. No. You have the microscopic and you have the purely agnostic. And the meta model is a kind of emulator of the microscopic model. Okay, so it is an emulator of the macroscopic model. So it is not an agnostic approach because you know the composition of matter. Okay, and it is a class of model that belongs to the density functional theories, and which capture in a quite analytical way the essence of your prediction based on the microscopic approach. So it's an emulator that speed up your macroscopic approach. Okay, so it's not an agnostic approach because you know what is the composition of matter, and all agnostic approach have a particularity that you are totally ignorant of what the matter is composed of. But in the meta model, you know. Yeah. Because, for instance, so this expansion is valid only for nucleonic matter. Okay, so and you have delta here, which tells you what is the asymmetry between neutrons and protons. Yeah, the proton fraction. So proton fraction gives you a composition. Okay, so you know if you have more neutrons or less neutrons, you know something. This information you don't have with an agnostic approach. Yeah. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. No, because it's not so. Maybe it's not really a Taylor expansion. Okay, it's a representation. It's a parameter expansion. So you wish to interpret these empirical parameters around saturation density, but this is a mistake. It does not necessarily translate the information. So that is something we realize because, for instance, we took a given equatorial state, we generate the empirical parameters of this equatorial state, and we put it inside the meta model, and we quickly realized that it is not a very efficient way to reach convergence. So the high order empirical parameters that are employed in the meta model may not be accessed by high order derivative around saturation density. So you should interpret them as giving you an information about dense matter. But you cannot determine everything from the knowledge of the derivatives around saturation density.
This means that you expand this as parameters.
Yeah, so the low order ones can be related to these derivatives around saturation density, but the high order one represents something different. I use the same, okay, yeah. Mm-hmm. Yeah, yeah, yeah. So but there is no experiments that could tell you what is the third or the fourth order derivative around saturation density. because you need to know very well. So it requires to reduce a lot the uncertainty in the lowest order empirical parameters that are quite difficult to reach. Okay, so it gives you a representation of the equation of state, but you should not interpret the high order empirical parameters as coming from a Taylor expansion and telling you what are the empirical parameters at high order around saturation density. It will tell you how the equation of state evolves at high density. Yeah. They are controlling so the high order parameters here that are there, for instance, they are controlling the high density equation of state, the way the equation of state behave at high density. And yeah, yeah, yep, 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 mm-hmm. Yep. Yep. Mm-hmm. 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 Yep. Mm-hmm. Yep. Mm-hmm. Yeah, yep. So yeah, maybe this is something we could discuss more among us. I'm not sure. I mean, maybe we are entering too much into the details. But what I would like to say is what you should still compare are functions of the density, and not necessarily empirical parameters. It works for the low order empirical parameters, but I think it doesn't work for the high order ones. Mm-hmm. Yep. Exactly. Yeah. Yeah. Mm-hmm. 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 Yep. Yeah. But I never say it's diagnostic. Uh-huh. Mm-hmm. 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 Yeah. Yeah. So it's a way to represent the equation of state. But what I say is that somehow at low density you could compare these coefficients with what I said before, which are the empirical parameters. But the high order ones, I think it is pretty unsafe to compare them to expansion around saturation density. This is what I observe from my experience on working on computing these empirical parameters from existing equational states. And therefore, I think that this is more the density dependence. So you could take a meta model and you represent how it evolves as a function of the density or the isospin asymmetry. And then this is a quantity that you should compare to the microscopic calculations, and not necessarily, you should not make a comparison of the empirical parameters at high order. Okay, so let's move on. For instance, yeah, so you can explore some uncertainties that you have on the way you parameterize a meta model, and look what impact it has on mass and radii of neutron stars. Okay, and on the left here, I show parameters for symmetric matter, and on the right, I show parameters for the symmetry energy. So for instance, you may say, well, I like to know more accurately the incompressibility of nuclear matter, because I believe that this has a great impact on mass and radius of neutron stars. You see, so I consider the variation of these empirical parameters inside the present knowledge we have. And you see that the impact on mass or radii of neutron stars is pretty moderate or pretty limited. So it's not null, but it's smaller than some other uncertainties that you may have on the slope of the symmetry energy, which will produce an uncertainty in the radius that is way larger than the one that you have for if you explore. So in this way, this plot tells you that the slope of the symmetry energy is a quantity which is extremely important to determine accurately if one wants to make an impact on radii of neutron stars. And and you can do the same thing with the curvature of the symmetry energy. So you see that it has a big impact. But for instance, if you continue the expansion, so you would say, well, maybe the skewness of the symmetry energy is also very important. But you see that, and it is a pretty counterintuitive argument, you see that if you go higher in your expansion, there is a natural cutoff which occurs and which tells you that you may not need to know more accurately the high order empirical parameters, because they're varying them inside some uncertainty will not make a big impact for neutron star mass and radii. And in a way, it is not very difficult to understand that, because the density in a neutron star are not infinite. They are limited. There are, you don't go to 40 times saturation density. Since the densities in neutron star are limited, it also means that this limitation introduce a natural cutoff in your density in your Taylor expansion or in your function expansion, because as it was shown before, you see the higher you go in the parameters, the more massive neutron star you need in order to make a difference. Okay, so if you know a radius for two times solar mass, you can raise this degeneracy. But if you know the radius for a low mass neutron star, then you see that the uncertainty in the radius is weakly correlated with the parameter that you vary. Okay, so in a way, if the density in neutron stars were infinite or very large, then you would naturally explore all these uncertainties that are in the expansion. But since the density are not so large, in fact, you can use this as a way to explore your uncertainty or to generate bands in the predictions. But you see that even neutron stars will not tell you a lot about high order empirical parameters. Okay, so this is in a way what I mean the interest of this model, which is that at the end the high order parameters allows you to explore some uncertainties and to generate some bands, but they are not crucial for the accurate determination of the radius. And yeah, and then the conclusion of this simple analysis is that there are three empirical parameters that are extremely important to know and to control, which are these empirical parameters. And they are not so high in the expansion, they are pretty low. So even though we may discuss and argue about the high order empirical parameters, at the end of the day, it doesn't matter very much. I mean, if you start to know these three empirical parameters, we'll start to discuss about them. But my point is, at the present time, we don't know very well these empirical parameters. So the QSAT, this is determining the density dependence of the incompressibility that we don't really know. LSIM is the slope of the symmetry energy that we may know, but finally with PREX or CREX, but finally we don't know very well what it is. And this quantity is the incompressibility or the curvature of asymmetric matter. And its determination is strongly impacted by the unknown in LSIM. We cannot really, I mean, from the breathing mode in finite nuclei, in asymmetric nuclei, we cannot really reduce this uncertainty if we haven't first reduced the uncertainty in the slope of symmetry energy. Okay, any question? Yep. 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 Mm-hmm. Yeah, so what I mean is here, so these cross here again are referring to the density that are in the center of a neutron star. And one means saturation density. Okay, so you see there that if you only use the properties of nuclei to determine the equation state, at maximum you reach saturation density, and therefore you cannot predict anything above half. For neutron star, you cannot predict anything above that. Okay, because your experimental data is limited to saturation density, and everything above is extrapolation. So and here, so at half solar mass, you are saturation density. If you go to twice saturation density, you are reaching one solar mass. Okay, so in a way, your nucleonic model, you need to be sure that the extrapolation from finite nuclei at saturation density towards twice saturation density is well under control. And if it is the case, then you could safely go from this point to this point. But I'm not sure, I mean, that data in finite nuclei could tell you anything about twice saturation density. So your extrapolation depends on the model. You may, however, employ heavy ion collision that will explore higher densities. Okay, but for the moment, it really depends. So what I want to stress is a link between the data that you employ, and you have to understand or to control. I mean, to really wonder these data, what densities they control, and if it is, I mean, data on finite nuclei, you have no everything at twice saturation density is an extrapolation. It's not in the data. It is beyond the data. Okay, so this is what I want to stress. But you may believe that, for instance, your model is compatible with heavy ion collision, and then you can go further. But you have to know what are the data that you put in your in your model, or that you employ in the way that you control the model to be safe in your extrapolation. Otherwise, it is unsafe extrapolation. Okay, so yeah, so time is flying. I still have several slides. Okay, so I will say a few words about Bayesian approach. It is, I mean, because it is very important in the way, in the modern way that we use in order to explore the uncertainty in the models. So it is based on the Bayes theorem, which tells you that if you want to associate a probability to a model and a set of data, okay, so you have to, so on one side, theoreticians, they produce model. On the other side, experimentalists, they produce data, and you want to put these two quantities together, okay? So you have two ways to do that. So either you have what is called the posterior probability, and you multiply this posterior probability by an information about your data, which is called the evidence. Or the same quantity, you may say, okay, I have a prior on the model parameters, so this is the theory part. And I have a likelihood probability, and when I do the product of the two, I should recover the same probability as when I do the product on the data, okay? And from this equality, you can determine this probability, which is the probability, the posterior probability, so associated, so the probability that you can give to your model. So the model are represented by a set of parameters which control your model, given some data. So this posterior probability, okay, which is the same quantity as this one here, you can say, well, because I have this equality, then this is my probability, knowing the probability associated to the data given a set of models, my likelihood probability, times my prior, the probability associated to the prior knowledge on the model parameters. And this quantity, this likelihood probability, you may employ a way to compare the data with model and say that, for instance, this is given by this expression for the log of the probability, which is which is very close to what people employ as a chi-square. Okay, so this is a difference between your data and your model prediction to the square divided by the uncertainty. And you have to sum over all the data that you have. Okay, so for all the data that you have and for which your model is able to predict something, you you can generate a kind of chi-square which evaluates the distance between the data and the model. And as I said before, not only you need to know the distance, but you need also to know about the uncertainty in this comparison in order to know if it is comparable or if it is different. And that gives you your likelihood probability. Okay, so the principle of the bias approach is to assign to a model given some data a probability, which is this one. And this probability is defined as a product. So this is not an exact way because you have to normalize your probability. So if you do that, you have an unnormalized probability. And the norm will give you the evidence. But so the bias theorem tells you that the probability associated to your model is a product of the prior that you can infer on your parameters. Okay, so for instance, you vary a parameter and you may say, well, I don't really know where it should be, but it should be between this value and this value. So you can say that I have a flat prior between these two boundaries, and then I have zero probability in between the two. So therefore, this quantity will be just a gate like that. Or you say, well, I have from a previous comparison to experimental data, I know that my probability, for instance, is a Gaussian shape, and therefore you may say, well, my prior will look like a Gaussian with a given distribution, and this is what you will put in your prior. Okay, so the prior is very important, and it depends on what you know a priori before you compare your model to some data, what you know about your parameters. And then there is this term, very important, which tells you, given some data, how close you are, how close your model can reproduce this data. And again, I stress that it is very important to estimate the uncertainty. Okay, well, time is going very fast. Yes. Well, for the Bayesian approach, you don't really need a package because you compare your prediction to data. So you can calculate chi-square. You don't really need a package to calculate a chi-square. However, you might need a package if you go beyond the Bayesian approach and you do Markov-Chain Monte Carlo, MCMC. So for that, you might need a package because so it is a metropolis exploration of parameters you reject or you accept. So I mean, it's a little more. So for that, there are several packages existing. But for the Bayesian, I don't use a package. For the Markov chain, so I use the EEMC, which is produced by the MIT, by a group in MIT. And so it is EEMC or EEMC2, I don't remember. And you have some documentation online. But it is only one example. There are several. And yeah, the Markov chain is really technical, and you may have different ways to do it. So yeah, so this is the reason why there are several packages. Okay, I think given the time, it would be. I mean, I can never stop. So I can speak during days. And there are a lot of materials that I haven't addressed and that are extremely important for neutron stars. So I think there should be a cutoff somewhere. I'm a bit frustrated that I have to stop, but maybe it is a good time, not a good point, but a good time just to stop and trying to answer some of your questions um, about neutron stars and yeah, dedicating this 10 or 15 minutes remaining to a more informal discussion among us. Okay, so I think it's better. Maybe, yeah. One last thing that okay, that you will find it in the slide that are online. So there are several things. So the last point I would like just to say as a conclusion of this lecture is again to show you the present knowledge and the present astrophysical data we have. Okay, so it's not a lot. Okay, you see that there are still big uncertainties, but if you imagine 10 years ago, we have no data, so it's already accumulation of the recent years progress. In the next 10 years, I'm pretty sure we'll have a lot more data. Okay, so this domain is changing and is evolving very fast. It is for the reasons I told you before. It is extremely dependent on the data. So if you don't have data, you don't really control the models. Okay, and the reason is that we have models, we don't have theories. We don't have a theory, we have different models. So we need data to control them. And the data, as you can see here, are not extremely good. So there are not points in mass and radius. So they might be a bit disappointing. But they are much better than what we had before without data. And in the future, we could expect that the uncertainties, first, the uncertainties in the data will be reduced and the number of data will be also increased. Okay, so I would like to use it as a conclusion of this lecture. And now, I mean, session is open for your questions. Thank you very much. Yeah, yeah. So, well, I mean, one kind of data which are very accurate are coming from radio astronomy, and these are the lower limit of the maximum mass. Okay, so if we could have a better, if we could observe more massive neutron stars compared to what we have now, that will make a clear improvement in the equatorial state and in the determination of the neutron star composition. Then I think that gravitational waves are maybe so they are here. They are. Oh, what is that? I don't know. So gravitational waves, ignora. So ignora per il momento. Oh. Ah. More. Okay. So this so for the moment we have only one data associated to this gravitational wave, and you see that it is not extremely constraining, but there is something, and why I believe it is very important and it will be very important in the future, is that the only thing you really need to impose in order to extract this data from a signal is that general relativity is correct. So in a way, if you assume general relativity is correct, then you can interpret the data, the waveform that you observe from the merger of two neutron stars. You don't need to assume anything else. Then you have the nicer results, which are given there. Okay, so there are two data. So you also need to assume that general relativity is correct. But it is also based on some assumptions about hotspots on the surface of neutron stars. And the uncertainty which that you see there also reflects the uncertainty on the position of this hotspot. And there is no, so the data, so you use some kind of Bayesian approach to match your signal with the data in order to infer this thing, but you don't have an additional data which could confirm either general relativity or the position of hotspots. You have to assume the two. So for this reason, I guess that it will be in the future pretty hard to reduce the uncertainty from nicer. But in the future, most probably the uncertainty that we have from the gravitational waves are essentially driven by the statistical uncertainty in the measurement. And with the improvement of the interferometers, so this was O2 measurement, and currently we are running O4 with better sensitivity. So if the same event repeats, of course, we have no control about the repetition of the event, but if the same event repeats, then this, with the present interferometers we have, so this uncertainty represented here will be something like that. Okay, so if we are lucky, if tomorrow there is the same event which repeats, we will have a much better uncertainty because it is only driven by the sensitivity of the detector. And of course, it is driven by general relativity. So if if any data tells you that it is wrong, everything that is there is wrong. Okay, but we may expect that if it is like the Newtonian gravity, it may be wrong, but for some extreme fields, that may not impact too much neutron stars. So for neutron stars, we may believe that general relativity is still pretty good. Yeah. Yeah.
You mentioned this quark star that can form a second prime.
Mm-hmm.
Which are the physical processes that can lead to a formation of strange stars? So, okay, theoretically, we can see that a quark star can exist from the model, but what is the physical process that can lead to a formation?
Well, the same process which leads to neutron star. So the question is, what is the equational state of matter? So if you believe quark stars, it means that you believe in the equational state induced by quark matter. And for that, you may have two ways to inject quarks in neutron stars. Either you assume that only some part in the center of neutron stars are driven by quark matter, and therefore you generate what is usually called a hybrid neutron star. So you have a layer of nuclear matter, and inside you have a transition to quark matter. So this is a hybrid neutron star, and then you have two branches, depending on the central density that you probe, or you create a model where neutron stars do not exist, but only quark star exists, and therefore you have a single branch, but you have to replace the branch for nucleonic matter. The prediction for nucleonic matter by a prediction for quark matter. So there are two ways to inject the quark matter inside neutron stars. And for the present time, we don't have data which are able to tell us if one of these two hypotheses is wrong, or even if the nucleonic hypothesis, the single nucleonic hypothesis, is wrong. So, so this is the reason why I wanted to finish with the data, because I think in the future we'll get better data, and by improving this data, we will certainly be able to give some better answer to your question. Yeah, you have a question? So you want to know if an agnostic approach is better than a microscopic approach, or? Yes. Well, you may yeah. So in order to answer your question, you may say, well, I select a given equational state generated by a microscopic model. You don't know if it describes reality or not. Okay, this is not the question. The question is how good, how it compares with an agnostic approach. And the point is that the two will generate a function between pressure and density, which could be represented by by one or the other. So you may generate this function from a microscopic approach. You may generate it from a mathematical construction, any of this agnostic approach. And if you really want to, and the agnostic approach will never, so depending on some of the question you have, you will use one or the other. But the agnostic approach will never tell you what is the composition of matter. So if you don't care about the composition of matter, you will be very happy with the agnostic approach. But if you want to know whether there is a phase transition or not, for instance, or what is the proton fraction in a neutron star, you cannot be satisfied with an agnostic approach, because the agnostic approach will never tell you if there is a phase transition, because it totally ignores the composition of matter. So if you know a little bit about microscopic approach, you may interpret some of the results of the agnostic approach. This is what we were discussing about in terms of phase transition, but the agnostic approach will never tell you anything about the phase transition, because it is not in the construction of the model. Okay, so yeah, I think it's maybe time to finish this, and I mean, I hope that the lecture was at a level that I try to make it for the people who are not specialists of the subject, and to understand what are the motivation and the scientific goals in this field. For the one who know very well the subject, they might be a bit frustrated because I haven't been so far in the description of neutron stars. But yeah, there are a lot of books, and I think that I mean, based on this simple introductory notes, you will be able to read books in an easier way. Yes, you have a question. What? What? Ah, is it raining on the neutron star? I don't know. I mean, I ask you this question. Yes, you're right. So did you? Yeah. You're right to ask this question. I forgot about it. So what is your opinion? I mean, is it raining on the surface of a neutron star? If yes, what may fall on your head if you were living on the surface of a neutron star? So maybe so we have seen that neutron star. Okay, they are made of a core and a crust. So in a way, they are quite similar to Earth. Okay, we have a core, a liquid core in Earth, and we have a crust, and we sit on a crust. Okay, if there were no crust, only liquid, we would sink. So in a neutron star is pretty similar. So what we have also on Earth is an atmosphere. Okay, and in a neutron star there is also an atmosphere. So one question is maybe what this atmosphere is made of, because it rains in an atmosphere, not in the crust. Okay, so what do you think the atmosphere of a neutron star could be made of? Okay, nuclei, yes. Which nuclei? Yes, helium, protons, helium, hydrogen, because they are the composition of the universe. They are, so imagine that you have a neutron star. The neutron star travels through the universe. So you have, it accretes some matter, and the material it crosses is interstellar medium, is mainly made of hydrogen and helium. So you may say that it is composed of hydrogen and helium. But you may also have a neutron star which has a companion. So we have seen you could have a white dwarf, and white dwarfs, they are made of carbon, oxygen. So therefore, the material of the white dwarf could accrete and also be employed in the composition of the atmosphere of a neutron star. So you may have a neutron star with a hydrogen atmosphere, with helium atmosphere, or with carbon atmosphere. So what if you have a neutron star, for instance, with carbon atmosphere? You have a huge gravity at the surface of a neutron star. So carbon might not appear in the same form as what we see on Earth. Diamonds. Yeah, so if we have, if a neutron star have a companion made of carbon, most probably it rains diamonds. So that's an answer. It's not the only answer, because it may fall also protons, less interesting than diamonds. But I mean, I think you may have diamonds that falls on the surface of a neutron star in some cases. And then the other question was about the mountains. So there were maybe two questions. So do you think mountains could exist? And if yes, why? And maybe the other question is if it exists, what, and this is what Ignazio, Professor Bombacci added to the discussion, if could you infer about the height of mountains? But then the first question is, do you think that there are mountains on the surface of neutron star? So you don't think so. So why? Because it's too massive, okay. But for instance, on Earth, if we had no crust, if we were on a boat and if we were living on boat on a liquid, so if there were no crust, only liquid, would the liquid resist to gravity? Would an Earth, where instead of having a crust, if we had just a liquid and we were, living in a liquid, would this liquid be spherical, or would we have mountains on top of a liquid? Waves? Yeah, okay. So what are the biggest waves on Earth that we have? Kilometers of waves? I never, no. Tsunami is maybe 10, 20 meters high, and it's enough to make catastrophes. When you have a wave of 10 meters in front of you, like in Japan, for instance, you may be scared. Okay, so you may have waves. So yes, and this would, so the highest waves you would have of the order of, several tens of meters. But the mountains, like Everest or others, are, 8 kilometers. So they are way larger than the waves. And the reason is that we don't sit on top of a liquid, but we sit on top of a crust. And a crust is a solid, and the solid could resist to some extent to gravity. So the question of are there mountains on top of a neutron star can be translated into, okay, we know that there is a crust. How strong is the crust? How strong the crust could resist to gravity? So of course, gravity will win, or gravity would like to have a spherical system. Okay, but you have a crust, so you can have some irregularities. And in a way, the question is, how strong is the crust? How strong can the crust resist to gravity that would like to make it round, but the crust could be strong and create some anisotropies. Okay, so the question about mountains is deeply related to the existence of crust. So if you had a liquid instead of a crust, you would have almost no mountains, or maybe waves. But the existence of mountains is tightly related to the fact that we have crust on the surface of a neutron star instead of a liquid. The book, the novel, yes, yes. Mm-hmm. Yes, correct. It's Robert Forward. No, the author is Forward. Yes. Mm-hmm. He was even he was working on gravitational wave, on resonance bar in the 70s, and he was a physicist who was trying to detect gravitational waves from compact stars. Mhm. Yeah, yeah, yeah. Yeah. Actually it's a very interesting book, and not only he mentioned about that, but he also tried to think about another question: is okay, if you find life on top of a neutron star, would it be life like us, or would it be ruled by different things? And what so our life, for instance, is controlled. So the time, our clock, our internal clock, is controlled by chemistry. Okay, by the speed. For instance, if we have muscles, okay, so the time that control our body and the way we could run and things like that is done by chemistry, so by reaction, by reaction between atoms. But on a neutron star, there is no atoms. There is only elements, ions and electrons. And in this novel, he imagined that the life was driven by electrons. And therefore, the clock, or the internal clock, so the speed, would be way faster, because the speed associated to transition between electrons would be way faster. And one thing which is very interesting, I will not tell about the end of the novel, but in the middle of the novel, so there is a space shift that humans decided to send to these dragon eyes, and they contain the encyclopedia, and therefore they send the human knowledge to the body that was existing on the neutron star. And since their internal clock were much faster, these bodies were able to understand, to read, to go further, and then they send back what they learned in a short time. And what they sent back is was said in the novel to be way beyond what we actually know, because they were very fast in learning and in going forward. Yes, you may. So there were clearly a mutual benefit from exchanging with people living on top of a neutron star, because they could learn our knowledge and they could give us back in a very short time something way more advanced than what we know. Okay. Yes, thank you very much.